Okay, so we just finished up 10.4, now we're on to 10.5. The title is Renewable Energy Available at an Acceptable Financial Cost. So, from what I've been reading over the past few decades, nuclear energy has actually become much more expensive. Regulations, waste disposal, et cetera, it's gone up by a factor of 3. Solar power, on the other hand, is just the bottom's dropped out of it, and it's going to keep dropping. Right here in the book, it says electricity generation renewables in the UK. It's been estimated that electricity from a new gas-fueled combined cycle gas turbine plant built in 2009 would cost. This is 6.5 pence per kilowatt hour. So that's only about 4 cents per kilowatt hour. That's the cost. Then the utility has to make money, and that's why we pay roughly double on that. And that says assuming a 10% discount rate on the capital repayments, which is, gosh, not too bad. That's a pretty good, that's a really good capital investment. And I don't roll in these circles too much, but you know, if somebody's putting a capital investment in an energy project is making 10% on their money, and someone who's doing it in real estate is making 4%, you know, you can see, and I don't know, it could be these numbers are inflated and unrealistic, but you could see how it would be more lucrative to put your money into energy rather than real estate. Figure 10.9, let's take a look at that. Yeah, that's what we were looking at previously. 10.9 shows estimated levelized costs of a range of electricity generating renewables. And let's just read through there. This is see Appendix B for a description of the term levelized. It's something that I kind of always need to remind myself. So let's just flip forward to Appendix B. It's right at the bottom of page 533. It says, one accepted method of making comparisons between such different types of plant is to calculate an overall levelized cost for the electricity in pence per kilowatt hour over the life of the plant. This is the value for the electricity spreads or levels. So it's got the cost of fuel, the operations and maintenance, the cost of capital, again, that paying back the 10%, and interest repayments across a given time period, usually for the life expectancy. It says, since inflation progressively erodes purchasing power of money over time, such an estimate necessarily has to be expressed in money of a particular year. So levelized means you're including everything in the overall cost. Okay. Now, it also says, as mentioned earlier, any fair comparison of fossil fuel, and I'm reading from page 473, should take into account a carbon price. The values used in the calculations in 10.9 that we're looking at right now, the carbon price, are on a sliding scale from 2009, rising in future years, but are equivalent to an average rate. Again, there's that 40 pounds per ton of CO2. So inclusion of a carbon price takes your electricity from 6.5 pence to 8 pence. What does that do? Well, I think it just has you wasting a lot less energy. You know, you go out and get the high efficiency light bulbs, and you go and get an app for your phone that allows you to turn your house off when you're not there.
I need that app.
I need the app. We're going to get the app. We're all going to have it.
So you say nobody's in the kitchen.
That's right. That's right. Okay. Prices, mass production, and perceived investment risk. So it says it's obvious from this figure 10.9 we're looking at that some technologies are far more expensive, yet they are supported because they may become cheaper in the future. So the idea is, hey, I'm gonna be the early adopter. I'm gonna be the Glenn Kreisel. I'm gonna go buy the Prius. When I put that money back into the Prius, or not, sorry, not the Prius, the Tesla, higher end, They put that money into the Tesla, and it allows Tesla to build more cars, work towards the Henry Ford mass production model, and then it sort of perpetuates that way. So you got to get it started somehow. It says, with the exception of the biomass example, and I know I saw biomass, oh, right here. It says, with the exception of the biomass example, the renewable energy technologies shown are all capital intensive. These technologies have reasonably long lifetimes, 18 years or more, fuel costs are zero, and the bulk of electricity costs are the repayments of the initial capital outlay. So, really all you're, well, not really all, most of what you're doing is just paying back whoever gave you the money in the first place. That's what those capital repayments are. Someone says, hey, I'm going to give you all this money, do your wave, it's going to take you a long time to pay me back, but obviously it's going to make some electricity, so there you go. Let's say offshore wind has been considered a slightly more risky investment, with finance likely to be available at a discount rate of about 12%. So, and again, I wish I understood the financial markets a little bit. So putting such a high rate, a high cost of the money, I guess that's what that's going to do to whomever is the developer of the energy technology. They're going to want to be a lot more careful with it, because it's just going to be that much more expensive. Any mistake they make is going to be even that much more expensive, because the money that they bought in the first place, or borrowed in the first place, is that expensive. Okay. Heat generation renewables, this is page 10.4. The natural gas boiler is pretty cheap at 6 to 10 pence. Air source heat pump, that's what we've been developing, and they haven't seen our technology yet, because they're saying we're looking at 10 to 16 pence per kilowatt hour. Our technology, let's just do it really quick for our solar thermal. So Missoula College solar thermal. What we spend on those exchangers during the practicum? $300, $500. Took so here's so this is going to be materials and supplies. I've done this before. Let's just say we're looking at about $300. Missoula College solar thermal labor. How long did it take to build those bad boys?
2 days.
2 days. So
Could have been done in one.
yeah, so we're looking at 2 days, which is 16 hours. Probably 3 people working. You built yours over there at Home Resource in
A day,
8 hours. So let's just say 40 hours.
7 hours.
Yeah, but for all 40 person hours, and let's just say $20 an hour, so we're looking at $800. Currency. $300, and then Missoula College solar thermal install. We put one in at Browning. You know, it took a little longer because we were doing the education portion of it, but I'm thinking 8 hours tops. So there's another 8 times 20. Well, yeah, and 20 is pretty low even. Let's say, you know, like if you're a professional trained installer, you're going to charge $50 an hour. So let's just say, let's just say $200. Okay. So what else do you have? You've got the the materials, the labor, the installation, so that's the total capital upfront cost. MC solar thermal capital equals sum, ding, ding. So it's a $1,300 system, let's just say total. And then how many watts are we looking at? Power, this is in watts. 2,000 capacity. Number, ding, ding, ding. Okay, 2,000 watts. I think the capacity factor, so Missoula receives about 4.4 hours of light per day, of full sunlight per day on average. So I'm just going to put the capacity 4.4, let's just say equals 4.4 divided by 24. So you're looking at 18% capacity. Control 1 number. Okay. Control 1, let's throw that as a percentage. 0 decimals. Fine. Okay. And then power watts. This is going to be power. I'll call it the nameplate power. That's what it's capable of. And then so its total power equals that times that. Control 1. Number. Watts. Okay. Still pretty good. You got 367 watt system. So now we're looking at cost. This is going to be in dollars per watt. Equals dollars per watt. 355. Not too shabby. I mean, solar panels themselves are 61 cents a watt right now. You add the inverter, you add the labor, you add the permitting. You're talking $3 to $4 an hour. But our little rinky-dink soda can is right on the mark. Now, let's go back to the levelized cost of heat from different sources. There is an air source heat pump, and this is pence per kilowatt hour. Okay. Man, I think ours is going to kill this thing. So now let's look at the lifetime. Let's put this in years. And I don't know how long these things are going to last. Maybe 10 years. Probably not, because they're just built with wood and they're built with the plastic, and you might have to swap them out. So let's just say 10 years. And let's just say kilowatt hours lifetime. So now let's take the power and take it from watts. And now it's going to be equal this divided by 1,000. 3 sig digs. So there's our kilowatts. Here's our lifetime in hours equals 10 times 365 times 24. So your system, if it lasts for 10 years, is going to be in operation for 87,000 hours. It's going to make, so now if we multiply, so this equals the, I'm getting you guys ready for 214, by the way. This is 214.
I want to learn how to use this thing.
Yeah, and I'm not using the whole, I'm using equals, I'm using times, I'm just kind of busting down the list. And the other thing I'm doing is I'm keeping track of my units. and I'm being generous and putting in sort of additional units conversions, things like that. So here's your kilowatts times your hours. So it's going to make 32,000 kilowatt hours of energy. And now let's look at the levelized cost. Having fun now. And this is going to be in, let's just do dollars per kilowatt hour. Dollars per kilowatt hour. Okay, now, do you have any operations and maintenance on your system? Yeah, maybe. Let's put that in here somewhere too. Insert before we do that. Let's just say O&M per year. And gosh, I don't know, let's say you have to maybe winterize it and you're spending maybe 10 hours total maintaining the system over the total year. So let's just say that's 10 hours per year. Insert O&M per year, O and M total equals 10 hours per year times total. And now let's do insert O and M cost. So somewhere up here, I probably should have put in an hourly rate. Let's just say 20 bucks an hour for that equals 20 times, this is, the units on here are hours. Okay, so you might spend $2,000 or $2,000 worth of time over the 10-year period. Control 1, currency, seems a little high, but that's okay. So the levelized cost in dollars per kilowatt hour equals the capital cost plus the operation and maintenance cost divided dollars per kilowatt hour. Here's your kilowatt hours. Boom. I did something wrong. Oh, I multiplied instead of. You got to know the difference between multiplication and addition. Just warning you. That's a big task. Okay. Control 1. Currency. 10 cents. Okay. Actually, we kind of hit it there. You look back at the table. They say air source heat pump, 10 to 16 pence per kilowatt hour, and gosh, we're about there. I thought it was going to be a lot better. I thought it was going to be like a penny or something. But looking at reasonable lifetime of 10 years. Okay, you're going to have to maintain it, paint it, whatever, get the bird's nest out of it sometime. 10 cents. So. Not too bad. Zero carbon. Okay. Take that to the bank.
Right.
Absolutely. Okay. I'm really glad we did that. Now, let's look at let's look at it's just called a marginal abatement cost curve for different technologies in the UK. And what we're seeing here is pounds of CO2 emissions. So I'm just going to read from the title. It says marginal abatement cost curve for different technologies in the UK. Domestic sector. This is not industrial for 2020. The UK total emissions for 2010 were almost 500 megatons, so 500 million, that sounds about right for the UK's population. So everything on the left is lifestyle measures, as well as lights and doing some insulation. So this is more or less reduction. You're gonna change your lifestyle and upgrade your electronics. This is sort of the amount of CO2 that will be reduced. These are all new technology. So here's, on the left is your conservation, on the right is your renewable technologies. Both will happen, and we can see that the more expensive are your PVs. I'm impressed that residential biomass is that cheap, but that's kind of where it is, and that's where I showed you that little shot of my basement. I'd like to be able to do biomass there and just get off the fracking grid. So that's one part of it as well. And then looking down here at table 10.1, we're looking at, now they're actually into cents per kilowatt hour. The best bang for your buck is hydro at 2.4 cents per kilowatt hour. That's what we see a lot of here in Montana. Onshore wind also quite cheap at 5.2. The biomass co-firing pretty cheap too, still at 2.9 to 7.1. Concentrating solar power, that's where you're actually making electricity. I gave a talk this morning in the recycling technology course saying that I'd like to see us going towards solar forges, so using just the sun's heat to melt metals as a concentrating solar, not to make electricity, but just to do manufacturing and recycling. That can be quite expensive, at least according to the authors here. Okay, and now what we're looking at would be a variety of large-scale renewables. And so this map is a lot like the map that I showed in the talk that I gave in Billings, where each state sort of has its optimal energy profile. And a lot of economics goes into this as well. I like this little box right here. This is approximately the 30 by 40 kilometer, the total area of seabed required to supply 10% of the UK's electricity needs. Pretty small. You multiply that by 10, and you're done. You got all your electricity from renewables in the UK. So it's happening. You got some deep water wave out there. They've got onshore wind, offshore wind. We've talked a lot about the coastal tidal. Those are there as well. So the thought has been done. A lot of the engineering has been done. Now it's just a matter of political will and financial investments to make it happen. Okay, a couple more figures. We're into 10.7 now. The next question says, are renewable energy supplies available when we want them? Okay, if you see one of these go up in the rattlesnake, you'll know it's mine. I'm going to build a little heat. It'll probably be underground though, but basically what they're doing, and this is just a model of distributed heat. And I don't know exactly where the energy for this comes from, but once you have this kind of infrastructure in place, maybe you're heating with gas, but then once you're concentrated solar, your biomass, you just pump your heat right to this bad boy, and that's a nice big tank. And there's your on-demand. There's your nice big on-demand. Everyone wants a great big shower. Well, you don't have to mess around with the little dinky tank in your house, and there it is.
Go ahead and do the dishes while I take a shower.
There you go.
Never had that problem.
Okay, now, this is a matter of time of day demand. And we can see, and this is gigawatts. So you've got a maximum winter, topping out at close to 60 gigawatts right around 5 p.m. or so. People are coming home, flicking on the lights, turning on the heat, running their garage door openers, cooking dinner, talking on their phones, what have you. You know, busy kind of rush hour for the whole UK. And then your lowest, you're looking at the summer right around 5:30 a.m. You know, it's still cool outside. It's probably already bright. People are asleep, so you don't have a whole lot of demand there. Everything's all good at 6:30 in the morning in the UK in the summer in terms of electricity demand. Okay, now what's also mentioned is diversity of demand, like all the different things that we use electricity for. And it says there are exceptions when the consumer behavior becomes synchronized. And what we see here is a little bit of synchronization with those peaks right around rush hour. They also mentioned that the history of the UK's natural grid was described in Everett 2012. It was initiated in the 1930s. It was generated locally in hundreds of small separate power stations with low average generation efficiencies. Now, we've got much larger centralized capacities. Everything's running at 50 hertz. So that will be a challenge if the grid goes global. You know, so right now we've got telecommunication cables under the seabed. I don't know how much those are used compared to satellite data, but if the grid goes global, it's going to be an issue because they're running 50 hertz and we run at 60. And maybe you need some kind of fancy AC transformer sitting out in the middle of the Atlantic somewhere to convert those two frequencies, because I don't see the standard changing. Just like it would be like changing which side of the road people drive on. Big system. Yeah. It says after experiments in 1937, it was found it was safe to connect together all the regional systems in England, Scotland, and Wales to a single national network. The output of individual stations was controlled centrally in order to optimize the overall system performance, and that's how it's been since 1938. Okay. The grid's been strengthened and reinforced since 1934. The main links operate at 275 to 400 kilovolts. Single lines can carry 2 gigawatts. 2 gigawatts, that's the size of Colstrip, which, big boy, it's about right. Overall philosophy, one large generating system to take advantage of economies of scale. Okay. Now, it says this is a picture of centralized generation. That's what we've been dealing with. Yet increasingly, there's a trend towards embedded generation. Smaller generators situated more locally up to the loads. And that's what we're going to see here in the U.S. And that's what, a lot of the off-grid folks are doing. It's kind of off-grid. I would rather not have my house be off-grid. I would, however, love to see our utility pay its customers when they make more electricity than they use. Hopefully that law will change soon. Okay. Oh, and here's a shot of it. I should have been showing this the whole time. So there's your central grid dropping down to 400 to 230 volts by the time you hit residential or industrial. Some of the heavier industries up at higher voltages. And then here are some of the distributed generation things that are coming online. So wind turbine, combined heat and power, kind of hitting the thing downstream where there's not quite as much voltage required. Okay. I think I'm going to stop there. There's still a few things to cover at the end of the chapter, but I think we've gone far enough. The authors do talk a little bit more about hydrogen later in the chapter, promoting renewables, looking at different scenarios, kind comes a little bit later. I will mention just a couple more things though before I let you go. Pump storage is one that's happening already with the Absaraka plant in Gordon Butte. Open cycle gas turbines, so that's another example of combined storage. We will in 214 do a compressed air energy storage. I'm now on page 486. Rechargeable batteries, a lot of money going into that field right now. And then it says which is best. Well, I'm gonna need them all. And then I guess I'll just look at one more thing so we can finish up this section. This is out of 10.2. So here's your open cycle gas turbine plant. 2 turbines, they run on light heating oil. And here, and I think now that we have so much information about the weather, we're going to be able to integrate our sort of big data information systems in terms of like where's the sun going to be, where's the storm going to be in a few hours. You know, we're looking at Birmingham, England. We're looking at Berlin with all of its renewable energy coming online, and this is going to make for a very interesting future of sort of trading renewables back and forth across this continent and storing them. We got the tides coming on twice per day, relatively predictable there as well. Okay, and that's I guess there's a couple more figures in this section, but we'll get into those on Thursday. All right. These are my kind of happy chapters. You get to see the future in a good way.
Is there a way you can get a copy of my license?
Yeah, let's do it. I hope that building next door is still unlocked. I didn't bring my keys. If you want to hop over there, Levi, and see if it's unlocked, 'cause I'm just going to try to shoot a print job to it. I can print that out for you.
Studying for finals and wearing me out.
Well, don't overdo it.
No, I'm on bed tonight. Well, not that I haven't gone to bed. I'm not staying up tonight. Tonight's my night. I'm like, no,
Snoozy time.
probably go to bed with my daughter at 8 o'clock.
Aw.
Climb in bed with her and say, let's do this. Wake up at 3 on my own bed. She's still little enough, she likes to cuddle still. So I soak it up while I can, until she grows out of it.
I know. Gotta love that.
Although all my other kids, no matter how big they get, they still want to hang on me. I don't know.
Say again.
My older kids, they're still cuddly.
Aw, that's good too.
Only when nobody's looking though. You know that. Well, I will see you Thursday afternoon.
Sounds great. Thanks, Shauna.
Yeah. Try not to work too hard.
Okay.
It's open.
Is it? Okay, cool. Let's see what I got for you here. Courses, documents. office. Students. Levi. Checklist, spring 16.
That looks right. The
Okay.
only thing is, I think I'm gonna do PV design, oh, you can't see it.
I can see it. PV?
PV design and install instead of alternative fuels.
Okay.
Uh,
This spring then, right?
Yeah,
Okay. Perfect. Okay, let's print this. File, print. Print that, and I'll print, print this. Let's just print this too. You know what, no, I won't, the registrar can see all that. You know.
Oh, right.
It's not required, it's just too much printing. Okay. Super.
And then you're gonna be in tomorrow for shells.
Yeah, I will. I was just feeling like dirt last week. Man.
Yeah.
Oh. You know, it's kind of funny, you know, like hearing all that stuff from Royce, at first it's like, really? Huh? And then you just kind of like,
Yeah.
so, yeah, I've got a couple things. There's actually a high-performance building social tomorrow. That should be kind of fun. I'll invite everybody to that.
Okay, what's that?
So there's a group, it's the same group I gave my talk to about renovating 8 Columbine. And they're here in town, it's a neat group of, movers, shakers, thinkers, doers.
Yeah.
So I'll forward that invitation too. Lots going on. Yeah, let's go make sure that printed.
On board and would love to help